All right. Hello, everyone. My name is Dima. I'm an assistant professor at NC State doing quantum photonics. And I'm going to present today with my graduate student, Abhishek Das, and with Kaixin Huang from Maryland. And we're going to talk about random pulse sequences for efficient qubit noise spectroscopy. So every qubit suffers from noise that leads to its decoherence. And our purpose is to characterize the power spectrum S of omega that dictates the decoherence due to the noise. So the way to do it, one way to do it is to apply coherent control of the qubit, apply pulses or continuous drive to control the qubit. And this pulses or continuous drive can be written as a function f. And then if we have a noise with spectrum S and we apply a pulse sequence with the function f, we can observe the dynamics of the qubit, which is denoted chi. So if we measure chi, and we know what pulse sequence f we applied, in principle, we can use this integral to extract the noise spectrum S. So the most straightforward to do it is to apply a control that is called CPMG. And CPMG is basically just a periodic application of pi pulses. What the CPMG sequence does, it decouples from the noise, but also it can be used for noise spectroscopy. What happens is that you apply sequences with pi pulses at different timings, and each sequence probes certain region of the spectrum, certain spectral area. So this is how you can apply different CPMG pulse sequences, either by changing the timing between pulses or the number of pulses, and you can probe different parts of the spectrum, and this is how you can extract the whole spectrum. However, there is a problem here. The problem is that this technique is not very resource efficient if our noise is sparse. If the noise is distributed across all the frequencies, then this technique works well. But what if the noise is only in a very, very narrow area of frequencies? Then this CPMG sequence will probe every single frequency. This is very resource inefficient, so it's not very good to use, let's say, if we want to use quantum devices and calibrate them and so on. So we need to come up with a better idea of how to extract sparse noise spectra that only have components with certain frequencies with a better method. And the better method is something that was developed by us together with Alireza Saif, Mohammad Hafezi, and our team with Kaixin and Nikailu. And the idea was published in a paper and PR applied last week, actually. The idea is that you can apply other types of sequences. It's random sequences. The pulses are generated in a random fashion. But essentially what it does, instead of probing particular parts of the spectrum, it generates some filter function that looks like cosine function that form a Fourier basis that each function probes the whole spectrum, but this whole process performed like sort of a compressed sensing. It's a more efficient way to probe spectra that are sparse. So if we talk about the spectrum that is ideally sparse, okay, has only noise at two particular frequencies, we can show that these random pulse sequences that form Fourier bases are able to extract the spectrum with much better accuracy and efficiency than other techniques. So now, here the seed grant comes. So what we wanted to do in this seed grant, we had three goals. Goal number one is to use these pulse sequences in experimental realization to probe the actual noise spectrum. The noise spectrum that we chose was self-assembled quantum dots. One, because one of the physical systems I work with is self-assembled quantum dots. And two, because the spectrum, the noise spectrum of these dots is almost sparse due to the interaction of the quantum dot spin with the nuclear spin. So this looks like this blue noise, as you can see here, blue spectrum. So my students, Abhishek and Michael, are working on this characterization. In addition to that, as you can see, our previous protocol's performance, shown here in red, sort of extracts the frequencies of the noise, but doesn't extract the noise completely. So we are developing, again, together with Kaixin Nikai, and we added a new team member, Dror Baron, who is from NC State, who is a professor and expert on compressed sensing. We are working on better ways to analyze and better ways to extract the noise spectrum, not just the frequencies of the peaks, but the whole noise spectrum in a more research-efficient way for practical applications. And other thing that we started thinking about, not quite finalized, with Norbert Linke is how to use this in other platforms like vibrational modes of ion trap. and other quantum Seal meters. So we haven't done much progress in the third part, but the first part, the experimental realization, Abhishek will talk about in a couple of minutes, and improvement and resource-efficient protocol for practical application, Kaixin will talk about it. So, please.
Hello, can you hear me? All right. Okay, cool. So now I shall be talking about the experimental realization part in this project. So first, I will start with the energy band diagrams of a quantum dot. So so there are four energy levels applied of a quantum dot applied under the application of a magnetic field. So you can see the spin eigenstates and also the trion states. So the red arrow shows you the optical pumping. So that's used for initialization purpose. And then you can also see the Raman rotation pulses that we're going to use for noise spectroscopy. So now we shall show you the step-by-step schematic of our experimental setup. First, we shall start with the cryostat, where we host the quantum dot in a cryogenic temperature. So then we apply these optical pulses, manipulate it, and direct it towards the cryostat through an optical setup, which is called an optical head. And for applying these optical pulses, we need a laser source, let's say number 2 or 1, doesn't matter much. So this laser source is for optical pumping that goes through an electro-optical modulator, and this modulator in turn is controlled by the pulses of arbitrary waveform generator. So the initialization pulses are basically on-off pulses. So we apply the same on-off pulses from the AWG, and these AWG pulses controls the modulator, and in turn it generates the pulsed laser pattern that we're going to use for initialization. And then we need another laser source for the rotation. So that laser source also goes through an electro-optical modulator, which in turn again is controlled by the AWG. So here we shall send sinusoidal pulses from the AWG, and the frequency will correspond to the energy gap difference between the spin eigenstates, as you can see here. So the frequency will be half this value to create two sidebands that are necessary to get this Raman rotation. I think some of you know about the driving to the detuned state, detuned by delta, and then achieving the rotation. So this we achieve by this laser source and sending the sinusoidal pulses from the AWG. And these sinusoidal pulses will be sent out following the random pulses that we have been talking about, and we shall show you the pictures and everything in a second. And finally, we collect the light from the cryostat. It goes through the optical head again, and we send them out for our optical measurements to spectrometer and single photon counting machines. And also, it's coordinated by another AWG signal. Now, we shall show you how much of this experimental realization we have achieved so far. So first, I will start with a picture of the cryostat that we're going to use. It's an RQS auto-dry cryostat, and this picture I have taken from their official website. So this is where we're going to host our quantum dot. And now I shall show you the picture of the optical head that we have already designed. We are using this Toptica DL Pro laser head, 930 nanometer laser head for the initialization and rotation purpose. And this little thing you can see is the electro-optical modulator that sits on a copper plate for temperature stabilized operation that gives you a high on-off ratio in high on-off extinction ratio. And finally, you can see the AWG. So, to send out the on-off pulses, the sinusoidal pulses for rotation and initialization. And finally, we do optical measurements with a spectrometer. Now, I want to show you that we have already achieved the sidebands that are necessary for the rotation purpose. So basically, just to remind you, we send out sinusoidal pulses to modulate the signal that's coming from the laser head. And This is the graph we can see from the spectrometer. So these are the two side bands, and you can see the modulation frequency is 15 gigahertz. It was rather random, but for our purpose, we'll tune it according to our application necessity. So yeah. Now I shall show you the important part where we actually program the AWG to get our random pulses. So as you remember, Dr. Farfurnik was referring to a function called f of omega t, which I refer here as t of omega. So this is the target function that we want to emulate through our random pulses. So basically, we want a window function that can closely emulate this particular target function. So the sinc square part is basically coming from the piecewise constant fashion of our random pulses. And Dr. Farfurnik already has mentioned about the Fourier basis that we're going to need to realize those random pulses. So our target will be to have an algorithm by which we can design the random pulses whose window function can emulate this function. So we have went on to design the, work on that algorithm, and the window function that we get are closely matched with the target function that we want. So we're good. So we can now use this window function to program our AWG and get the random pulses out of it. And we have achieved the random pulses like shown here on a MATLAB plot. So you can see the blue pulse, that initialization pulses. You remember those are on-off pulses only used for driving the qubit to a particular state. And these are the rotation pulses that we're gonna need. And the timing of these pulses are dictated by the random pulses that we care about. And finally, we have also experimentally realized those pulses that you can see on the oscilloscope. So the time duration is much longer than what we're going to use in our real setup, for the sake of visualizing it on a low frequency scope. So thank you. So I'm going to pass it to
All right. So thanks, Dima and Abhishek, for their great job on building the lab. So I'm going to talk about the update on the theoretical perspective. So you may remember, last year, I gave a brief introduction about this random power sequence method, and it is actually a very general protocol, a very general toolbox. And compressive sampling is one of its most important applications. And actually, we have done some experiments on trapped ion and superconducting qubits, and the results are pretty good. But we are using some manually injected noise. So we are still very excited to see how our method works on some realistic spectrum, like this quantum dots spectrum. So as you can see, as Dima already explained, it's pretty sparse. And according to our methods, we are able to characterize the central frequencies of the spectrum, as indicated by those red dots. And we can further compare the accuracy of this method with the normal CPMG method. So for example, here, the y-axis describes the accuracy in the central frequencies, and the x-axis describes how many resources you will need it. And that is proportional to, that includes the time you will spend in each single experiment and the total repetitions you will need. And it's very interesting that for the compressed sensing method with random pulses, you will see a clear phase transition compared to the normal CPMG method. And according to our theory, the total resource you will need is proportional to log n, where this capital N represents the total resolution of your noise spectrum. And this S represents the sparsity of your spectrum. For example, how many peaks are there in your spectrum. However, there are still some problems that we can improve. So the first of all, the most obvious one is that the realistic spectrum are not ideally sparse. So as you can see, those spectrums are more like a combination of some separate mountains, and they have some specific widths, and also they have some slow decaying background. And our previous method just took this slow decaying background as some background noise, and we are totally lost those informations. So we would like to see how we can improve on that. And the second problem is that in realistic worlds, we usually have some limitations on the total number of policies that we can apply in a single experiment. And well, this might not be a feature, in the future, but right now we do have this problem. And to solve this problem, we have developed a new method called like uncorrelated random policies. But since the time is limited, I will only cover the first problem. I will describe how we deal with the not ideally sparse situation. And the solution turns out to be quite simple. So actually, we don't need to change any settings for the experiment. You can run the same random policy generator as before, and we are still probing the spectrum in the theory basis functions. And the only thing we need to change is the post-analysis part. So instead of assuming our spectrum to be ideally sparse, we are assuming, we are mimics it as like a piecewise linear function. And intuitively, it's not that different from the previous case because a piecewise linear function, it's still sparse, but in its second order derivatives. And that's why we would use the second order total variance regularized lasso to solve this problem. And it turns out that we could, in principle, extract those zigzag features of the quantum dot system. And this looks pretty nice. And the problem is like, what is the efficiency of this method? Will this be worse? And again, we can compare the accuracy of the method with CPMG, but this time we are much more greedy because we want to find all the details of the noise spectrum. So we are using the L2 norm of the noise spectrum as an indicator for the accuracy. And it's pretty good. And you can see we still find this phase transition curve for the random policies with compressed density. And compared to CPMG, we still have a very great speed up. And we can theoretically prove that the total results we need is still proportional to log n. But the constant S star is a little different from the previous case. So in general, this S star describes how well you can approximate your noise spectrum as a piecewise linear function. And we can continue to do those simulations for spectrums with like under different conditions. So for example, we can simulate spectrums under different magnetic fields. And so those blue curves represents a theoretical backgrounds, theoretical noise spectrum of the quantum dot system, but it's coarse grained. And we can even add some readout errors to our simulations. I mean, these errors are pretty big. It's like 5%, but still, our reconstructed spectrum matches almost perfectly with the theoretical result. So that means our method is actually quite robust. And this is very nice because, compared to the previous case, we are not only probing like the local maximums of the spectrum, but also like the local minimums of the spectrum. And that is very meaningful because you can use that to do noise suppression. So remember, people originally proposed dynamical decoupling such that you can find some frequencies where the noise spectrum is very small and you can do a spin lock such that your qubit will only react to the certain frequency such that you can suppress the noise. So that basically concludes my part. And yeah, maybe you might want to summarize?
Yeah, basically the summary is on the board. We have progress in experimental realization as well as in the theories of the analysis. And we actually want to conduct all these experiments, implement all this analysis technique, and adapt this to other systems and quantum simulators. Thank you all.
Thank you.
We have time for one question.
Thanks for the great talk. I just wanted to understand better what is random about this protocol. It seems you have a target filter function and you just deterministically optimize it.
Oh, yeah, that's a great question. So the basic idea is very simple. So remember, this is so the decay rate X can be expressed as a linear integral of your noise spectrum and some, let's say, window function F. And the idea of the random pause is that you can generate some random pause such that the average window function will be exactly the target function, function you want. And in that way, you can probe arbitrary linear functionals of your noise spectrum, and you can use that to do a lot of different things. So that's like the basic idea.
How is it different from like having multiple window lengths of CPMG and having these like deterministic set of?
Yeah, for CPMG, it's deterministic, and for random policies, every time it's a little different, and you need to generate a group of different random policies, and their average window function will be the one you want. But the thing is that you don't need to repeat experiments on each sequence a lot of times. You just need to apply some trial experiments on a single random pause, and then repeat these experiments on a lot of different random pause sequences. And their average will give you the exact result.
So as you can see here, the randomness comes from a different spots in which you randomly choose whether you apply a pi pulse or not. But it's not 100% randomly. There is some algorithm that we're using that if we apply those bunch of random pulses that obey to this algorithm, we effectively get the window function that we want.
Now, in other words, like the correlations between those random pulses are like finely detuned. Yeah. It's not. It's right now. It feels like a black box to you, but you can check the paper. Yeah.
Swing the speakers.